Good afternoon, everybody. I hope you're doing okay. Today will be fairly short. I'm going to go back quickly over what we did last time and do a couple of examples, and that'll be it pretty much. Let's see. Good. All right. All right. So we've defined the notion of double integral, and it's a sine volume. And we've defined the notion of iterated integral. And Fubini's theorem says that under certain conditions, we can compute the double integral using these iterated integrals. So let's just go back to this briefly. So I want to compute the double integral of a function f over a rectangle, let's say AB times CD. And Fubini's theorem says that under certain conditions, then this will be the same as the following iterated integrals: integral from A to B, integral from C to D, f of xy dy dx, or in the other direction, integral C to D, integral A to B of our function f dy dx. And so we need some conditions which are technical, and we're not going to go into the technical version, but recall that it suffices that f be continuous on the rectangle R, except for a set of measures 0. Which I've defined, which is a bit tricky. So think, for example, a curve. Okay, so next class I will I will use this so that we can integrate over more general regions. I don't want to start this today. I just want to give you a couple of examples again. So that's Fubini's theorem, okay, which tells us how we can compute an integral over a rectangle if the function is nice enough. We saw a couple of examples already, right? So we saw that the order in which you choose to integrate might be important, right? So we had this example where we were asked to compute the double integral over a rectangle of y sine of xy, right? So it's easier because of the function, right, of the shape of f to compute the integral. So sorry, I didn't say what the rectangle is. So the rectangle is 1, 2 times 0 pi. So this is the last example I did last time. And so it is easier to do it in this direction. So 0 to pi, 1 to 2, y, sine of xy. Oops. Sorry. Dx, dy. And the reason being that if you look at the inside integral, which is always the first one that you're going to do, so here, y is a constant, so integration is easier, okay? So if you try it in the other direction, you have to use integration by parts. And in the second integral, it gets also messy. So in this direction, this is easier. Okay, so now I want to do two examples. One which is very concrete, but it's a bit involved. And so there's some calculations that we have to do to see exactly what's going on. And the second one is actually easier, but it's more theoretical, but we'll use it later on, okay? So now two examples. Okay. So let's set up this this first example, which is the following. Okay. So example one. So we're asked to find a volume. So find the volume of the following solid. It's called S, doesn't matter, which is bounded by the following surfaces. So it's bounded by, first of all, an elliptic paraboloid. Ooh, no, yes. You'll see it's not so bad. So elliptic paraboloid, x squared plus 2y squared plus z equals to 16. It's also bounded by the planes x equals to 2, y equals to 2, and the three coordinate planes. Okay, so, all right, so a question I often get is, do we have to be able to draw this? The answer is, in theory, no. In practice, if you can, it's going to help a great deal. Okay. So, so let's try to see what this thing is about, or at least maybe not draw, you know, like a really super nice picture, but you have to at least have some idea of what's going on. Okay. So, so that's the question. So what does this look like? Now, if you remember Cal 2, when you were asked to find an area, the idea was always the same, is you're given a bunch of curves. I should write this. So recall Cal 2, finding the area of some region, right? So you were given a bunch of curves which bound a region. And what did you have to do is basically you have to set up an integral to find your area. So the idea was set up the correct integral, right, to compute. That's always the idea. Okay. So this is the same thing. Basically what we want to do is to find, so here's the same. So find function f and region. So in general, it could be some complicated region. For now, it has to be a rectangle, right? So here, a rectangle. Okay. So we have to find the function f and the rectangle so that the volume of S will be the double integral over function f over the right rectangle, right? So that's the game, okay? And then, of course, to compute the integral, but that's a different issue, okay? So this is what I need to do from the information. I have to find the correct function f and the correct rectangle and set up my volume as the double integral of that function over the rectangle. No more coffee. All right. So let's cut and paste this. Copy and paste. Okay, so this is the question. Okay, so the question is, what does S look like? In other words, what I want, so find F and R, right, for my integral. Okay, so let's start with this elliptic paraboloid. You can probably guess that the function will come from that surface, right? So what does this thing look like? So it's an elliptic paraboloid. You see there's the z there that's not squared. So you can solve for z, okay? So this is the same as z equals to 16 minus x squared plus 2y squared. Okay, so why am I writing it this way? You'll see in just a sec. So to sketch this, here's how I do it, okay? So first of all, you see that this thing is just some function shifted up by 16. There's a plus 16 there that just shifts up your whole the graph of your function. So that's nice and easy, right? Then you have that minus sign. What does a minus sign do? It flips your graph, right? Up and down. So here's how I'm going to see this. So consider z equals to x squared plus 2y squared, right? So that's the inside part of my bracket, which is multiplied by minus 1. So this one, I know pretty much how it looks like, right? So what does it look like? I'm not going to worry about the elliptic thing. I'll just see it as a circular. It's the same thing, right? So basically, this is, think of x squared plus y squared. Z equals to x squared plus y squared. What is that? It looks something like that, right? Roughly, okay? Now, what happens if I multiply by minus 1? It'll flip it downwards, right? So z equals to minus x squared plus 2y squared. You flip. So now it's going to look like that. Hopefully, everybody is okay with that. Right? And then finally, I'm going to add 16. So this is going to shift up the whole graph by 16. Finally, add 16. So shift up. Okay, so I'm going to go to the next slide for this. Let's copy this down. Yeah, I feel like copying the whole thing, but okay, I'll just take this again. Okay. So again, so before I switch, so I'm looking at my elliptic paraboloid. I want to see what it looks like. And so I started with z equals to x squared plus 2y squared, elliptic paraboloid going up. I flip it down by multiplying by -1, and then I'm going to shift up by 16. Right? This is my question again. So if I shift up, so it's going to look something like this. Okay, my picture is pretty ugly, but okay, you see what I'm saying. Okay, so your elliptic paraboloid I looks something like this. Okay, so it's an upside down paraboloid shifted up. Okay, so now we're starting to have an idea of what the graph of the function could be. It'll probably be the function whose graph this is. So it looks like f should be, so it looks like f will be f of xy equals to 16 minus x squared plus 2y squared. Okay, we'll confirm that in just a second. Okay, so now what I'm looking for is my rectangle over which I am integrating. Okay, so this will be given by the second and third parts. So the planes x equals to 2, y equals to 2, and the 3 coordinate planes. Okay, so the 3 coordinate planes, there's the xy plane, xz plane, yz plane. So you see that you're going to be in the first octant, right? So so the solid S is below the paraboloid and between the coordinate planes, right? So it's going to be somewhere over this part somewhere, but we're going to find the rectangle and under this curved surface, right? Okay, so this is where online teaching is like not really so, I mean, it's not so good in any case, but here I'm having a lot of trouble. Okay, so we need to find the rectangle. Okay, so this will be given by the planes x equals to 2 and y equals to 2. So let's see, I'm going to redraw this thing. Okay, hopefully I can switch slides right now. Ah, yes. Okay, so my picture, I'll try to do it a little better now. So I don't need to bother about, yep, I can. Oh, I went too far, right? Sorry. This is what you want. All right, good. Okay, so again, as I said, because we're looking at the coordinate planes and the planes x equals to 2, y equals to 2, I actually, what I said wasn't exactly clear. but because of the planes x equals to 2, y equals to 2 will be in the first octant. Sorry, so we needed that condition to make sure we're in the first octant, but it's going to be somewhere around here, okay? So now, doing this in 3D is tricky. So what I'm going to do is simply look at the xy plane from the top, okay? So look at, as usual, right? So x, y, and you have to imagine your surface is above here. So now I'm looking at x equals to 2 and y equals to 2. I have these planes like that. The coordinate planes, this one, and now, so here's the only tricky part, which is a bit annoying, is where does that ellipse hit, right? So if we're really unlucky, so imagine that the ellipse were actually inside that rectangle that we see, then we'd be in trouble because the solid wouldn't be well defined. But in fact, we're going to be okay. That ellipse is going to actually hit outside here, okay? So we need to make sure that it doesn't cross the rectangle. Okay, so let's say that you're doing like a super important exam and you know for sure that the problem is going to be given over a rectangle, then you don't really need to check, right? But this is not going to happen because later we'll be integrating over more general regions, so you'll have to check somehow, okay? So simply check that ellipse. So what is this ellipse? It's where the elliptic paraboloid hits the xy plane, right? Intersection of paraboloid with the xy plane. So simply check that the ellipse is outside the rectangle. And then we'll be good, right? So it means that this rectangle given 0, 2 times 0, 2 is the region over which we're going to integrate. So how do let's just do that, okay? So it's just some simple algebra, but I have to check it. So how do I find the equation of this ellipse? Okay, so all right, so this ellipse here, star, right? So how do you find that? So what is this ellipse? It is the intersection of your paraboloid with the xy plane, right? So this is intersection of x squared plus 2y squared plus z equals to 16 with the xy plane. What's the xy plane? It's z equals to 0, right? Okay. So if I give you two equations and you want to know the intersection, you're looking at the points that satisfy both equations. In other words, x squared plus 2y squared plus 0 equals to 16. So that's the equation of your ellipse. Okay, so that's the equation. I'm only looking at part of it. That's the only part I'm interested in. Okay? And now I want to make sure that this rectangle is inside. Okay. Well, all you need to do is this. So let's just, hopefully I can switch slides soon. I have no water and no coffee to pace myself. I'll just do that. Okay. So there I go. Okay, so x squared plus 2y squared equals to 16. And hopefully, okay, the rectangle is inside, okay? Here's rectangle inside, okay? So here's the trick. So we're going to set x equals to, well, okay, yes, let's play with this just a little bit. We'll set x equals to 0 in here, okay? We're going to get y squared equals to 8, which means that y is square root of 8. So this is the point here, it's square root of 8. This is bigger than 2, okay? So 2 is around here. So far, so good. Set y equals to 0, you're going to get x squared equals to 16, so x equals to 4. So 2 is here also. Am I safe? Maybe not. What could happen is you have something that looks like this. Right? That would be bad for us. So how am I going to check this? There's a simple way. Okay, so look at this line here and see where it hits here. See where it hits here. And if this is bigger than 2, then we're fine, right? So simply check. X equals to 2. Okay, so if I set, I'll get 4 plus 2y squared equals to 16. 2y squared equals to 12. Y squared equals to 6. This is bigger than 2. This is great. Y equals to 2. That's x squared plus 8 equals to 16. So x squared equals to 8. So x is equal to 8, which is bigger than 2, and we're happy, right? So these two values are bigger than 2. So the point 2, 2 is inside. All is good, okay? Okay, so rectangle is completely inside ellipse. Okay, so it's exactly like the picture shows. Okay, so now what is the solid? The solid is everything above this rectangle under the surface. And so we've set up our integral. Okay. Hopefully you can visualize this. Okay. So let's write it out. Okay. So solid S is the region below paraboloid over rectangle, which is 0, 2 times 0, 2. In other words, the volume of S is the double integral over this rectangle of our function f, which we wrote, which was 16 minus x squared plus 2y squared. Okay. So that's by definition of the integral. It's the sine volume, but here everything is above the xy plane. And so now I can use Fubini. Why? Because this function is a polynomial, so it's continuous everywhere. So no problem. So by Fubini, this is an iterated integral. and I can choose whichever I want. Now, if you look at this polynomial, it's basically symmetric in x and y. Okay, there's this coefficient of 2, but it's not going to change anything. So you just pick one of them, and it's going to be fine. So integral 0 to 2, integral 0 to 2, 16 minus x squared plus 2y squared, let's say dx dy. Again, you can choose or order, no difference. Okay, so technically it's not going to make any difference. Okay, so again, so when you have an iterated integral, you start on the inside, first of all, so I'm integrating with respect to x. So this is my outside integral. So if I'm integrating with respect to x, this is 16x minus x cubed over 3 minus 2y squared x, right? Y is a constant. This is between 0 and 2. So I've just computed the inside part using the fundamental theorem of calculus. Okay, just evaluate at 2, evaluate at 0, and subtract. Okay, so this will be 32 minus 8 over 3 minus 4y squared. And when I plug 0 in, everything disappears, so I don't need to, I'll just put minus 0. Like that. Okay. And so now we're down to the second integration. Okay. So now I integrate with respect to y. So this is 32y minus 8 thirds y minus 4y cubed over 3 between 0 and 2. Okay. I could have computed 32 minus 8 thirds, doesn't matter. And so this will be 64 minus 16 over 3 minus 32 over 3 minus 0. If you plug in everywhere, you're going to get 0. So this is 64 minus 48 over 3, which is 16. And so this is 48 units, whatever. Okay. All right. So to recap, you're given, sorry. Is it possible in any way that after doing the first integral, we still have two variables? No, impossible. Because if you still had an x, it means you didn't evaluate it properly, right? Let's go back one slide. Oh, 2 slides. Right? So when I'm computing the first integral here, I'm integrating with respect to x. I use the fundamental theorem. So y is just there for the right, just a constant, but I'm evaluating all x's at 2, all x's at 0, and subtracting. So no, you can't have any x's left. That's a good question. Can both variables disappear? Yeah, so look at, in this example, if the function didn't depend on y, then that could happen. Look at the first part, which is over here, right? So then y would disappear. I mean, there's no y to start with. But if there was a y in the original function, you'll have a y left, unless maybe stuff could cancel out. I don't know. Yeah, exactly. So yeah, so we'd be left with the second integral of the constant. This could happen, absolutely. Rarely, but it can happen. It means you had a really super simple function. Yeah. Okay. This wasn't the hardest integration in the universe, right? It's just simple polynomial. So the hard part is not the actual integration, it's setting up the integral. But if you remember from Cal 2, that was often the case, right? So although this is actually more demanding, it can get pretty complicated geometrically because you have to sort of visualize things in 3D. In Cal 2, it was just flat. Usually it's not so bad. You have to do some algebra to intersect curves and things like that, but it's not so. But here there's more things flying around, okay? We'll try to keep it not too nasty, right? Okay, so this is a pretty good example. It's from the geometric point of view, it's like moderate to slightly difficult one because you have to figure out if the surface goes inside that rectangle or not. Okay, so it turned out to be okay. So if there are no more questions on this one, I'm going to move on to my second example. This is taking longer than expected, but that's okay. All right. This one is pretty short. So if the surface goes inside the rectangle, then there are a couple of ways you could do it. So at this point, we don't know exactly how to do that, but there are a couple of ways you could do it. The first way, once we see what we'll see Wednesday, would be to change the region of integration. It won't be a rectangle, it will be something else, and we'll see how to handle those. The other way, well, that would be the way. Yeah, I don't see another way of doing it. Yeah, so we don't, this exercise was set up to work with what we knew, right? So, so we expected the rectangle to be inside otherwise. Yeah, so the question is, can we cut the region in two pieces? Yeah, so this is one of the tricks that we'll see. But you have to be careful here because once you're integrating over the rectangle here, if the rectangle were going outside, you'd get some negative volume because your surface would be below it. That would be tricky. That would be a very tricky question. Okay, but we'll see how to handle regions like that starting on Wednesday. Okay. All right. Okay. So now here's my second example, which is actually a result, which is somewhat useful, but it's really cute. So example 2. So this is actually like a 2-line observation or proof. But I'm going to use, so there's something that I want to do in a couple of weeks, which is to show you a proof. Don't be scared, it's just a computation. Or the computation of an integral, but it's a one variable integral, but there was no way we could have done it in Cal 2, but it's a really fundamental integral, which if you're doing any sort of statistics right now or have done statistics, you have seen this curve at least 10,000 times. But to compute the area under the curve, the tools that we had in Cal 2 were not sufficient, but somehow going to 2 variables will allow us to find this integral, which is really cool. And one of the things that I need is my next example, which is slightly related to one of the questions about the variables disappearing. Not quite, but it looks a bit like that. Okay, so here's here is a property of very specific functions, which is this. So suppose that your function f has a very specific shape. It's the product of a function of x with a function of y, which doesn't happen very often, right? So suppose it is g of x times h of y. So if you look at the previous examples, they didn't look like that, okay? Then, oh, sorry, I need a rectangle. Let's say my rectangle is AB times CD. So if your function happens to be the product of a function in x and a product of a function in y, then the double integral of this function over a rectangle splits as a product. Okay, so then the double integral over r of f of x, y is equal to the integral a to b of g of x times the integral from c to b h of y. Okay, and I want to show you why this is true. Okay, so again, if you happen to be very lucky and the function you have to integrate is a product of x stuff and y stuff, then you can actually split this integral into two parts, the x part and the y part. Okay, so y. Let's see. Okay, so I want to show this. Okay. I want to verify this. Okay, so I'm going to start with this side. And yeah, I didn't put the hypotheses, but I'm allowed to use Fubini's theorem. The function f is nice enough. Okay, so apply Fubini. So what does it say? It says this double integral of f is equal to double integral from a to b, double integral. You know what? Wait. I want to do it the other way. I'm going to write it this way. Okay? So I'm just applying Fubini. There's nothing, I haven't used anything about the function f. Okay? So what is that? I'm going to replace f by what I'm told it is. And I'm told that it is a function of x, g of x, times a function of y, h of y. Okay? All right. So now, how will we compute such a thing? You look at the inside part. Okay, I have to compute this integral. Now, what is h of y in this integral with respect to x? It is a constant, right? So what can I do with a constant? I can factor it out. So h of y is constant with respect to x. So I can factor out of the inside integral. So this is the integral, c to d, h of y times integral a to b, g of x, dx, dy. Okay? And I don't know if anybody can see the last move to checkmate this thing, but it's pretty cool. So look at the inside integral there. That's just an integral, right? From a to b of a function g of x. So what is that? That's a number, right? That's a constant. What can you do with a constant inside an integral? You can factor it out. So you factor out. So that you're allowed to do that. So what is that? I factor out this constant, integral a to b g of x dx. And what's left is the integral c to d, h of y dy. And that's what I wanted. If that looked mysterious to you and it looks like I just sort of put back the cut card and you said, oh wait, there's a trick. No, there's no trick, really. It's just we're applying Fubini and we observe that because the function is a product of a function of x and a function of y, things magically happen. So you can actually factor out the h of y from the inside integral, which is an integral of x. And once you've done that, the integral of g of x dx, that's just a number, so you can just take it out of the outside integral and you get exactly what you want. Okay? So that's sort of cute. Not super useful, by the way, in terms of the chances that you see a problem. I mean, you might see one once in a while, okay? But they're rare. I mean, you're not gonna see this kind of function very often. But I'll need it in a very nice computation at some point, so I wanted to do it and show it to you because it looks good. Okay, so let me just add that in. So not used often. But I'll need it when I compute the area under the normal curve distribution. Let's put it this way, right? So you probably have seen this before, but right, this thing, I'm going to compute the area under this curve a little later on, and I'll need this trick because to do this integration, the simplest way to do it is to actually look at a problem in 3 dimensions and get back this. I'll do that in a couple of weeks. Okay, this is the end for today. Unless there are questions, comments. It's all good. Yes, thank you. Excellent. Yeah, okay. When we'll have the exam? That's a good question. I'm still undecided. Likely something around the 19th or 20th, something like that. But it could be the week before. I just need still to see where we're going with this. If you have it's harder than when we're in class, so I can poll everybody at the same time. But if you already know when you're going to have other exams, 20th would be great. Okay. So yeah, so send me some messages. I will not be able to satisfy everybody, but if I have get a bunch of people telling me please don't put it on the nth for some n, then I'll avoid that date, right? But we have some flexibility. So if you have preferences, but I don't need preferences to send, like, Tuesdays I'm watching this show, that's not good, right? But if you have, I already have an examiner, so that's exactly it. So if you have, please not 20 specifically, okay, all right. But this chat I will say, but send me messages telling me, okay, this date I already have an exam, so then I can get an idea, and then we'll try to fix something, okay? But please don't, the chat here, I'll have a copy, but send me a separate message so everything will be in the same place, okay? So yeah, all right. So that's your homework, okay? Send me your preferences for not this date or prefer this date, okay? All right, so I'll see you on Wednesday. Goodbye.